Hello, this is Brad Stribig. Today we're going to talk a little bit about how fish breathe. I suppose part of this is because I like to go fishing and I enjoy seeing beautiful fish. These are brook trout that are shown in a limestone creek in the Shenandoah Valley. Limestone creeks are typical of cold, spring-fed water, in this case that comes out of a spring and also off of a deep water reservoir that feeds this small creek in the Shenandoah Valley with cold, fresh water. You can see on these rocks, though, that there is a little bit of algae growing, so there's light penetrating the water where these fish are habitating. One of the important values of these cold water streams is indeed the temperature of the water itself, because that affects the level of oxygen that's available. And trout, as a species, the fish shown here, are very sensitive to the level of oxygen in the water. So in this example, we're going to use Henry's Law to show how fish breathe. In nearby Mossy Creek is a famous trout fishing stream in Virginia. In this area, there's actually a tourist-based industry built upon the trout that live in these streams. Trout generally need about 5 times 10 to the minus 4 pounds of dissolved oxygen to remain healthy per cubic foot of water. This is a very cumbersome way of describing how much mass of oxygen is needed in a given volume of water. So let's look at some different ways of expressing this. Although not conventional English terms, the units of milligrams per liter are much more common. So let's calculate from the values above how many milligrams per liter of oxygen that's dissolved in the water, called dissolved oxygen, easily enough, is required for a healthy trout population in these Virginia streams. So here we have our value of 5 times 10 to the minus 4 pounds per cubic foot of water, and there are 35.31 cubic feet per cubic meter. There's 1 meter cubed per 1,000 liters, so we can find liters in the denominator, and there are 454 grams per pound, so we multiply the 5 times 10 to the minus 4 pounds of oxygen, convert that to grams, and then multiply by 1,000 milligrams per gram, and that gives us the answer that we see below, which is for trout to remain healthy in cold water streams, they require about 8 milligrams per liter of dissolved oxygen. The solubility of compounds is the amount of a substance which can dissolve in water. This can be a solid substance, like sodium or chlorine, but it can be gases as well, like oxygen and carbon dioxide. So the concentration of the pollutant in the gas and the liquid phase are linearly related, and this relationship is known as Henry's Law, where we have a given value of H. In this textbook, we're going to use Henry's Law units that are equal to the atmospheres divided by the mole fraction. The mole fraction can be expressed as Xi, the liquid mole fraction. All Henry's Law constants have units, but these units may vary. So if you find Henry's Law values in a different publication or different textbook, check the units carefully to make sure that the units are consistent with those that you're using. We'll also see that the Henry's Law value varies with temperature. The concentration in the water grows larger as the temperature cools. Eventually, this relationship becomes non-linear, but for our purposes, we can see that a linear relationship is true across a relatively broad environmental temperature range for oxygen and carbon dioxide. So these are two terms that we're very concerned with, oxygen and carbon dioxide in the water. And in your textbook in Table 2.3, list Henry's Law values, again, in units of mole per liter per atmosphere for these compounds, for dissolved oxygen levels and dissolved carbon dioxide levels. And we can also see that as the temperature decreases, the concentration of oxygen and carbon dioxide in the liquid phase will increase. So if we go back to our example for trout in Virginia, let's see what happens if we want to incorporate this into a business model. There's a trout farm nearby for a local farmer who wants to diversify his farm business in his pond by creating a pay-per-catch trout farm near Mossy Creek. He wants to raise trophy trout, but the water temperature in his pond in July and August averages about 77 degrees Fahrenheit. Knowing what you know about the minimum oxygen levels for trout and the relationship between temperature and the concentration of dissolved oxygen, do you think this is a good business investment or not? So what we want to do is find the dissolved oxygen level in this pond water when the water temperature is at its highest values in late July and August. So the first step is going to be to convert the degrees Fahrenheit to degrees Celsius to find the Henry's Law constant from the previous table. So to convert degrees Fahrenheit to degrees Celsius, we subtract 72 degrees from the Fahrenheit degrees and multiply it by 5/9. Conveniently, this gives us a value of 25 degrees Celsius. We can also look at Table 2.1 to obtain the partial pressure of oxygen in the atmosphere. If you recall, we said that the oxygen in the atmosphere makes up about 21% of the atmosphere. At standard conditions, the standard atmospheric pressure of all the gases combined is 1 atmosphere. So the pressure value for the part of the atmosphere that's made of oxygen and the pressure that that oxygen exerts on every other substance, both humans and the water, is going to be 0.2095 atmospheres over the surface of the planet. This is a level at sea level, but we're pretty close to that here near Mossy Creek. Next, we'll determine the Henry's Law value from our Henry's Law table, Table 2.3. We'll use the Henry's Law value of the oxygen, H sub O2 in this case, and the partial pressure, P sub O2, multiply those together to determine the liquid concentration of oxygen. From our table, at 25 degrees Celsius, we see the Henry's Law constant for oxygen is 0.0012630 moles per liter per atmosphere. Now we can solve for the liquid concentration of dissolved oxygen in this pond. We substitute in the value for Henry's Law, which is 0.0012630, and I like to think of these units as that's going to be moles per liter, our liquid concentration, over atmospheres. We multiply by the composition of oxygen, the partial pressure that it exerts on that water body, which is 0.2095 atmospheres, and we get a value of 0.0002646 moles per liter. We now have units of moles per liter. What do you think is the next step? It should be obvious by this time we're going to do a unit conversion from moles per liter to milligrams per liter. So we take the value of the dissolved oxygen in moles per liter, 0.0002646 moles per liter of dissolved oxygen. We multiply by 1,000 millimole per mole and 32 grams of oxygen per mole, or 32 milligrams of oxygen per millimole, will give us a value of 8.467 milligrams of dissolved oxygen that are available. So we can see that there is sufficient oxygen over the summer months for the trout to be healthy, but we are indeed very close to the threshold. That's why north of Virginia, these trout farms in cold water streams are fairly common. But as we go to Maryland and Virginia, that's about as far south as we find cold water trout ponds, unless they're cold water spring-fed ponds where the water is unusually cold for a given condition, perhaps high in the mountains of North Carolina or Georgia, where we find these trout streams, and not near sea level, and not so much in the Midwest. In the next section, we'll go on to describe more chemical applications and how we look at the ideal gas law to determine where concentrations of species are in the environment.